In this video, we'll find the horizontal wind pressure and associated drag force using AASHTO. And remember, this is not directly comparable with the ASC7 method because AASHTO uses different load combinations and a variety of different load factors for wind. So we'll start with equation 3.8.1.1-1 for VDZ, or design velocity of the wind at height Z. So that's our VDZ. Our V naught is our friction velocity. Our V30 is our 30-foot wind velocity. Our VB is our base wind velocity. Our Z is our height of the structure, and Z naught is the friction length. Now we'll take our 30-foot wind speed as our base wind speed of 100 miles per hour, and we'll use the same assumption of 50 feet as the height of the structure. And with a special note, friction velocity and friction length are meteorological wind characteristics, so based on a certain topography, taken from table 3.8.1.1-1. We'll use open country conditions, so we get a V naught of 8.2 and a Z naught of 0.23 to solve for a design wind speed at height Z of 110.3 miles per hour. And next, we'll navigate to equation 3.8.1.2-1 for design wind pressure. This is how the wind speed actually translates to force on the structure. So our base wind pressure comes from table 3.8.1.2.1-1. And remember, we're treating our surfaces as flat and adjusting for the actual solid area using that ratio we came up with in the previous lecture of epsilon, which is our solid area to our gross area. So we're going to take this value of PB, our base wind pressure from the table for large flat surfaces, as 0.04 KSF. Now plugging in all of our variables gives us a value for PD, or design pressure, that we can convert to a line load in kilonewtons per meter using that effective area and any associated load factor. And note that these load factors, this load factor will change based on the associated load combination you are using. You can find these combinations in table 3.4.1-1 for all the various limit states as defined by the AASHTO specifications. And the factors are associated with different combinations with dead load or live load or other loadings on the bridge, and the probability you're going to experience that magnitude of wind in that moment. So on a final note, if we apply the ASD primary load factor, we get approximately 0.6 kilonewtons per meter, which is much closer to our 0.5 kilonewtons per meter wind load from Helvetas. And if we take our design velocity down to 30 feet, which is probably more realistic for these bridges, this comes down to exactly 0.5 kilonewtons per meter. So now back to that final note, in section 3.8.2, the AASHTO specifications discuss vertical wind pressure, or a minimum uplift. This minimum uplift is 0.2 KSF along the bridge deck. So a 1.04 meter bridge deck will give an uplift along the deck of approximately 1 kilonewton per meter. Because this can be applied at what is called the windward quarter point, torsion can occur along the deck, so think flipping of the deck. We won't analyze uplift in various load combinations or this torsional instability and the associated flutter effects because these are negligible for most suspended bridges under 120 meters. The Logan-Bertling thesis that we have mentioned in the introduction portion of this module and linked goes into detail on these calculations, which should only be considered for long span bridges or uniquely windy sites.